say that chemistry's my hustle, and your brain is like a muscle. So settle in because it's time to flex. Hey everyone, welcome to day 10. Today we are going to look at more acid and base stuff. This is our second part, and specifically we're going to look at how pH is impacted by not only the concentration of the solution, but also whether it's a strong or weak acid. And I want to start at the back here. I added a little bit of notes. You can write this in to help yourself out here. There's 3 parts. In our first part, I just want to look at some strong acids and strong bases. There aren't too many of them, so we're just going to write down the ones that there are. As far as strong acids, I don't know if I even have a good way of remembering this. This is just a short list that I tend to remember. But, you know, if we look at our periodic table, there's a little funny little trick. I don't know if it actually is useful for you, but take these 3 elements and then take these 3 elements. All of our strong acids deal with these elements here: nitrogen, sulfur, chlorine, bromine, iodine. So let's go back and write out the ones that we have. One strong acid that you might recognize is hydrochloric acid. It's a pretty common strong acid that we use in the chemistry lab. You've done labs with hydrochloric acid before, and I've warned you that they are corrosive. There's also a couple other strong acids that are just hydrogen with another element: hydrobromic acid and hydroiodic acid. What those 3 monoprotic acids, monoprotic meaning 1 hydrogen, those 3 monoprotic acids each have halogens as their anions: chlorine, bromine, iodine. They are all halogens. There are some other strong acids though. For instance, there's nitric acid, which comes from the anion nitrate. There's sulfuric acid, which comes from the sulfate ion. There's perchloric acid, that comes from another one that has chlorine in it, except this time the anion is chlorate. These 6 acids are what we call strong acids, and we will talk about what strong acid means in just a second. As far as strong bases go, for your list of strong bases, just think about your alkali metals. You know, these ones over here. I'm leaving hydrogen out, not a metal, and I'm leaving francium out because it's not stable. These 6 elements, or these 5 elements, when coupled with a hydroxide, are strong bases. So let's list them out. I'll use blue: lithium hydroxide, sodium hydroxide, rubidium, I guess I can list them in order: potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Those are alkali metals that are hydroxides, and they're strong bases. So when a strong base or a strong acid is in water, the thing that makes it strong is the fact that it totally dissociates. We're going to write out the dissociation of a strong acid in water. Let's write out an acid, and for an acid, I'm just going to write HA, and that A just stands for anion. It's anything with a negative charge, any negatively charged ion. When that reacts with water, it's going to act like an acid, and it's going to donate a proton. And it donates its proton to water to become a hydronium ion. And there's our anion that's left over. For a strong acid, 100% of that strong acid dissociates. And I'm using dissociate in the same way that we learned it in the context of electrolytes, as in like solubility. It totally breaks apart in water. Same thing goes for our base. When our base reacts with water, 100% of it is going to do what a base does, which is it's a proton acceptor, right? So 100% of that base is going to accept a hydrogen and dissociate into a hydroxide. Notice the H2O is breaking apart. It's autoionizing. The base is gaining a hydrogen, and the hydroxide is turning into the water is turning into a hydroxide. Now that might seem a little confusing because I didn't include a hydroxide, but I could show you this another way. What if I did this? What if we just got rid of the water part and we looked at an example that had a hydroxide, like a base hydroxide? It's still 100% dissociating, and we have a base with its positive charge, and then there's our hydroxide left over. You can think about it either way. This way might make more sense since we're talking about strong bases with their hydroxides. Totally dissociating. So what does it mean for something then to be a weak acid or weak base? Remember our lists up here? These are just the strong acids and strong bases. Any other acid or base is going to be weak. So it's the majority of them. For an acid to be weak, we still write the acid as HA when we're trying to show it symbolically. We can still include water. And the funny thing is we're still going to produce some hydronium ion, and we're still going to be left over with some anion. But how much? I'm going to draw a double-sided arrow here, and I'm going to write a lot less than 100%, closer to 1%. Okay, so not much of this is going to dissociate. Same thing goes for our base. Let's stick with the base hydroxide that I drew in the second one up there. So double-sided arrow, because a lot less than 100% of this is actually going to dissociate into our base ion and hydroxide ion. So to give you an example, sodium hydroxide is one of these strong bases. We know that 100% of it dissociates into sodium and hydroxide. Ammonium, though, is a weak base, so only some of it is going to take in a proton. Let's visualize this, and I think it's going to help to see what's going on. There's a simulation. This PhET simulation is nice because it allows you to see the ions. And in this case, I'm not even showing you the solvent. You remember that the universal solvent is water? So there's water everywhere in here. Well, even water dissociates to some small extent. But notice that we have equal number of red H3Os. These are hydronium ions. Anytime you see a red one, just think acid. And every time you see a blue one, think base. We have two little acid, whoops, I touched the wrong thing there. We have two acid ions, two hydronium ions, and two base ions, which are hydroxide ions. Since they're equal, that's why our pH is 7. What would happen if we have a strong acid? Notice that, I'm going to get rid of our water now. Notice that everything is dissociated into red the red hydronium ions, and then we are left over with some A-. These are our anions that are negatively charged. Our pH is 2 because this is a strong acid. It's totally dissociating. It's based on the number of hydronium ions that are in concentration. Make a guess about what's going to happen when we look at weak acids. Notice with weak acids, we have a lot more of that HA in solution. In other words, and this is a big takeaway in this one, for weak acids, they don't dissociate to the same extent that strong acids do. We have less hydronium ions in solution, less H pluses. And that's why our pH is 4.5, whereas with our strong acid, our pH was 2. So that's one of those funny things with pHs, is that something with a lower pH is a stronger acid. Or it's more acidic is what I'm trying to say. Let's look at bases now. All right, for the strong base here, we see everything on the screen right now is M plus or OH minus. So that's our hydroxide ions, those purple ones. That's what makes a base a base. When we look at weak bases, though, only a small percentage of them are actually dissociated. I think an easier way to look at this might be to take a look at a graph. Notice that for this weak base, a large majority of it is still in its reactant phase. It's still B and H2O. But if I switch back to strong base, we don't have any of our strong MOH base left in solution. It's totally dissociated into M plus and OH minus. Same thing goes for strong acids. We don't have any HA left in solution because it totally dissociates. For a weak acid, though, we have plenty of HA left in solution because it doesn't totally break apart. Okay, let's look at a separate one. One more thing I'd like to show you. Right now we are looking at a weak acid. The pH is 4.5, and I'm able to change the concentration. Watch what happens to the pH when I change the concentration. I'm going to increase the concentration. As I increase the concentration, what's going on? Well, I'm adding more HA, which in turn means that some of them are going to dissociate. What happens to our pH if we have more H3O that's dissociated? Well, the stronger the acid in terms of concentration, the lower the pH. The same thing goes for base. Let's make a base now. Let's take a base and let's make it stronger. Predict what you think is going to happen with pH when I make the base stronger. Did you guess that the pH would increase? Well, when you think about strong bases, I want you to think about approaching 14, because that's what's happening is we're increasing the concentration of our base here, is that the pH is going up. If this had been a strong base, more and more of it would have been dissociated into the BH plus and OH minus. Let's look at acids again. Here's a strong acid that's totally dissociated. And let's actually just change its concentration is pretty close to 0.1 right now. If I reduce, or not reduce, if I change it from a stronger acid to a weaker acid, I'm not really changing the concentration of the solution, but I am changing the concentration of the H3O. I'm reducing the amount of H3O that's in solution, and therefore the acid is weaker, and that's why our pH is going up. Take a look at this solution's pH. This is a pH strip. We could use this and determine that its pH is in that, what's about that 4 to 5 range. But if I make it really strong and we check the pH again, now it's closer to that 0 to 1 range. Because it's a stronger acid, that means there's more H3O plus solution. Oh, and one more segue. because we did talk about electrolytes before, this is an example of an electrolytic solution. If we have a strong acid, it totally dissociates, and therefore we have lots of ions in solution. Right now we are allowing lots of current to transfer through this wire. It's an electrolytic solution, so it conducts electricity. But if I reduce the strength of the acid, I am also reducing the number of ions in solution, and so less and less electricity is able to be conducted. There's still some ions in solution, so the light bulb is still lit to some extent, but not as much as when we have a really strong acid.